Welcome, this is the Vika Academy, and we are looking at Cayley-Hamilton theorem. If you have not subscribed to this channel, kindly subscribe, and remember also to share with your friends. So this topic today is a very beautiful one, and it's about Cayley-Hamilton theorem. And remember, this is the Vika Academy. So what does this theorem state? Cayley-Hamilton's theorem states that every square matrix satisfies its characteristic polynomial. Every square matrix, as far as you are dealing with a square matrix, then its characteristic polynomial is satisfied. What does that mean? It means if you substitute the matrix to its characteristic polynomial, the solution will be definitely 0. You will get 0. That's simply what Cayley-Hamilton's covered. And we have now Cayley-Hamilton theorem. Let's look at a demonstration through an example. So we're having a hair here, which is one of the square matrix. It's a 3 by 3 matrix. Now let's first get its characteristic polynomial. The characteristic polynomial for this A is actually given by this from our previous topic. So if you have not catched that previous topic, kindly just go back and see how the discussion was. If you find something that you are not able to link up, kindly leave a comment there. I'll be grateful to be back to you. Okay, so that determinant for this determinant here for the definition is actually this. So that the characteristic polynomial for this is actually this. Now, our discussion in Cayley-Hamilton theorem is just to show that this particular characteristic polynomial is satisfied by the matrix A. So this will be able to write this as in where we have x, we replace with our matrix A. So we'll have A power 3 minus 10 10A, not x in this case. Wherever we have x, we put A plus 1. We just need to show this by Cayley-Hamilton's that this gives us 0. If that happens, then we will have shown that the Cayley-Hamilton theorem is actually the truth. So this follows. Remember, wherever you have 1, while you are using the matrix, you are substituting with this one with identity matrix. Then remember, if you want to get A cubed, you are basically doing this multiple multiplication. The matrix A, you multiply by its matrix A and again by matrix A, which is like doing A squared times A. You'll be able to get A cubed. I have also done this in a previous tutorial. You can see how we do multiplication for matrices. If you find any question, just leave a comment. I'll be able to look at it. So going back to this, now substitute back with your value of A cubed, A, and identity. This definitely will give you 0. And that justifies what Cayley-Hamilton discovered. Remember to subscribe. Remember also to share with your friends. Let's look at another definition here. So we are having a square matrix A. Then the monic polynomial of smallest degree mx, for which ma is equal to 0, is called the minimum polynomial. So this definition here is basically for minimum, what we normally call minimum polynomial. It's for minimum polynomial. So if you have this particular square matrix A and it has a monic polynomial of a smallest degree mx, and you find that this mx, which is again a special kind of quadratic polynomial, its ma is equal to 0 by Carley-Hamilton. Remember, this is an extension of Carley-Hamilton. Then that particular mx will be defined as minimal polynomial. It will be the minimal polynomial for this particular matrix A. Note this: the matrix satisfies characteristic polynomial which is monic by Carley-Hamilton theorem. So that the existence of minimal polynomial is that guaranteed. As far as we can recall Carley-Hamilton, then the minimality of the polynomial x is justified. It's already guaranteed. If you have any question on any point, kindly just leave a comment. I'll be able to check it back. Okay, let's have a claim then. The minimal polynomial is unique. Let's see, if we claim that the minimal polynomial is unique, can we be able to prove this? So this is how we do it. We know the minimality of any polynomial is guaranteed by Carley-Hamilton's theorem, because we know PR, the quadratic polynomial of A, will definitely be equal to 0. So its existence is there, that the minimal polynomial it exists by the function that Carley-Hamilton theorem exists. So what do we need now? We need to introduce two different minimal polynomials, which is minimal polynomial 1 and minimal polynomial 2. We just need to show that these minimal polynomial 1 and minimal polynomial 2, as far as for one polynomial or from one square matrix, then they are same thing. They are same thing. They are not two different minimals. If we can prove that, then we have shown that the minimal polynomials are unique. So let's do this. Let's take the degrees. We know the degree for the polynomial. A polynomial of A, quadratic polynomial of A, in terms of x is n. Why are we saying it's n? Because whichever we are having here, we are having a polynomial, quadratic polynomial for a matrix, a square matrix, which is n by n, and therefore the degree of that matrix is actually n. It's n. Therefore, its polynomial again will be to that particular power, n. Therefore, the degree for minimum 1, polynomial 1, will be equal to the degree of minimum 2, because we are getting them from the same matrix. But they can be either equal or less than the degree of the matrix, or the degree of the many polynomial. So it will be less or equal to n. So let's introduce something interesting here, and I have also did this one in previous tutorials, and you can look them at it from previous tutorial. And if you have any question again, just leave a comment. I'll be able to check it. So by division algorithm on the polynomials, we know this will be true, that the polynomial m2 will be equal to the minimum polynomial 1 times the quotient plus the remainder. That's definitely an application of division algorithm. So if we introduce the decrease concept here, degree of the polynomial will be definitely less than the degree of m1. So what does this mean? It will mean that if you can write this in terms of a remainder, you'll see that this is m2 minus m1 times the quotient. So that now, this is the polynomial characteristics based on x. If you reduce A, the matrix, then this concept will be true. But there's something we know. We know these have same decrease, and therefore, by again Cayley Hamiltons, this part will tend to be equal to 0. This will be equal to 0 by Cayley Hamilton, because the polynomials of characteristic polynomials will be equal to will satisfy the rules of the square matrix. Will be satisfied, so it will be equal to 0, and therefore you can see that will be true. So that if then the remainder of x is not equal to 0, and by the divination we have seen that proven that Ra is equal to 0, with degree x of the remainder being less than the degree of m1, then that will be definitely become a contradiction. And this will be a contradiction of minimality of degrees of m1 and m2. So that gives us with no other option except that Rx should be equal to 0 and m2 can only be written in terms of mx and the quotient x. So, but the degrees of m1 and m2 are both are equal and are both monic. That will mean that because the degrees of m1 and m2 are both equal and they are both monic, then it will mean that m2 and m1 are same thing. And by that fact, our claim becomes true that the minimum polynomial is actually unique. Okay. So, if you have not subscribed to this channel, kindly leave a subscribe. Remember also to hit the bell button so that every time I post anything here, you'll see the notification. So we have another claim here that if you are having an n by n matrix, a square matrix with a minimal polynomial ma and a characteristic polynomial pa, if fx is any polynomial with fn being equal to 0, then it will mean that again this minimal polynomial will divide fx. That is true. And again, the minimal polynomial always divides the characteristic polynomial. So that's a claim and can be proven. So let's prove this. So by divination, we know minimal polynomial and the fx, the function x, is equal to 0. And we know the degree of fx is greater or equal to the degree of mx, the minimum polynomial. So by division algorithm, fx can be expressed in terms of mx, qx plus rx. We know that can be expressed like that. But we know the degree of rx is less than the degree of mx. So that it will mean that fa and MA quotient of A and RA is true, that's true, like that, and 0. Remember, this is the FA is a polynomial, okay? So it will give you FA will be definitely be 0, MA will be minimum polynomial will also be 0, and that will indicate clear that the RA is actually equal to 0. And if there is no remainder, it will mean that it will be able to divide. Our function because the remainder is not there. So if the degree Rx being less than the degree of the minimality, minimal polynomial, and if Rx is not equal to 0, we have a contradiction, remember, and Mx is a polynomial degree of Rx equal to 0, and Fx equal to Mx from Qx, which will mean that it will be able to divide because there is no polynomial, and this is by benefit of Cayley-Hamilton's theorem. So that's 22. That's 22, and that is the end of that proof. So if you have any question on these matters, kindly just leave a comment and I'll be able to check on it as much fast as possible. Remember to subscribe if you have not yet subscribed, and also remember to share with your friends. Remember, this is the Academy.